BYU has developed an innovative model known as A3B. Its full name is a bit of a mouthful, but the idea behind it is brilliant and straightforward. It's a mixture of experts, or MOE model. This means that while A3B has a substantial 21 billion parameters in total, only about 3 billion of them are actively engaged for each task or token it processes. Think of it like a specialized team. Instead of having everyone work on everything all the time, a smart router decides precisely which experts are needed for the job, keeping compute costs low while still giving you the benefit of highly specialized knowledge to prevent these experts from all converging on the same solutions. The team implemented clever training tricks like router orthogonalization loss and token balance loss, ensuring true diversity in how the model learns and activates. BYU's researchers argue that 3 billion active parameters per token might just be the sweet spot, enough power for serious reasoning without making the system so enormous it becomes impossible to train or deploy. And here's a crucial point. A3B is open source under Apache 2.0, meaning anyone can access it from Hugging Face for research or even commercial products. This level of openness is a huge deal, especially when many other powerful reasoning models are locked behind APIs or proprietary systems. A3B also boasts an impressive context window, capable of handling 128,000 tokens. They achieve this with a clever technique, progressively scaling rotary position embeddings during training. Combine that with flash mask attention and memory-efficient scheduling, and you get long context training that doesn't demand impossible hardware. The model was trained with a meticulous pipeline, starting with text-only pre-training, then moving to supervised fine-tuning on math, logic, coding, and science, and finally progressive reinforcement learning. They even used a unified preference optimization method, which blends preference learning with PPO, helping to prevent reward hacking and making the AI's alignment more stable. But A3B isn't just about generating text. It comes with built-in structured function calling, meaning it can call external APIs or tools while reasoning. This is a game changer for complex tasks like program synthesis or symbolic reasoning, making A3B a highly practical option for multi-agent workflows and enterprise systems that need both long context understanding and the ability to interact with the outside world. Its performance across logical reasoning, math, scientific questions, and programming is exceptional, demonstrating stable accuracy on long chain of thought benchmarks. BYU is making a compelling case. Frontier-level reasoning is achievable without entering the trillion-parameter territory, all with an efficient, open, and long context-ready design. Now, while BYU explored the power of sparsity, another innovator took a different, yet equally impressive approach. Let's look at K2 Think from MBZUAI. Instead of going sparse, MBZUAI went dense. K2 Think starts with a 32 billion parameter backbone, then layers on a heavy post-training pipeline and an inference scaffold. Their achievement is remarkable, taking a manageable base model and, with the right recipe, getting results that rival systems many times its size. K2 Think's training pipeline is a masterclass in AI development. It begins with long chain of thought supervised fine-tuning, essentially feeding the model countless examples of step-by-step problem-solving in math, code, science, and general chat. The goal is to teach the model to show its reasoning, not just spit out answers. The gains from this were immediate and significant, with accuracy on tough math tasks climbing sharply, even before reinforcement learning was applied. Then came a truly novel approach to reinforcement learning. Instead of relying solely on human preferences, MBZUAI introduced verifiable rewards. They built a dataset called Guru, with 92,000 prompts across 6 areas: math, code, science, logic, simulation, and tabular data. The crucial difference is that the model is rewarded for answers that can be objectively checked as right or wrong. This makes the learning signal far more reliable, drastically reducing the chance of the model cheating the system. They also discovered that starting this reinforcement learning process earlier, closer to the base model, yielded massive improvements. It's about finding that perfect balance between initial fine-tuning and room for robust reinforcement learning. What makes K2 Think feel truly agent-like is its behavior at inference time. It doesn't just dive into a solution. First, it writes a short plan, like an outline. Then generates the full answer. After that, it produces a few different possible answers and runs them through verifiers to determine the most likely correct one. The outcome? Not just better accuracy, but surprisingly, shorter, cleaner answers. A rare feat, as more steps usually lead to wordier outputs. The performance figures are astounding. On tough math benchmarks like AIME and HMMT, K2 Think achieves exceptional scores with significantly shorter responses. On OmniHard, one of the most challenging math benchmarks, it scored over 60% while shrinking answers by nearly 12%. This combination of high accuracy and leaner outputs is almost unheard of. It also excels in coding on live Codebench v5, outperforming larger models while cutting response length. Its science reasoning is equally strong, proving it's a versatile powerhouse. And it's not just smart, it's robust and safe. K2 Think has strong scores in macro safety, refusal, conversational robustness, jailbreak resistance, and cybersecurity. All of this is backed by incredible speed, thanks to speculative decoding and Cerebrus wafer-scale engine hardware, pushing out around 2,000 tokens per second. That's production-level throughput, not just research speed. The real kicker? K2 Think, at just 32 billion parameters, achieves all of this while competing directly with models like DeepSeek v3.1, which has 671 billion parameters, and GPTOs at 120 billion. That's parameter efficiency that fundamentally redefines what's possible, hinting at a 100 times more powerful paradigm shift. And just like BYU, MBZUAI has embraced full transparency, releasing weights, training data, deployment code, and test time optimization code. This level of openness is invaluable for researchers and offers enterprises another powerful open option beyond proprietary APIs. The message is clear. The AI industry is witnessing a profound shift. The race to build ever larger models is being challenged by innovative approaches that prioritize intelligent design, meticulous training, and efficiency. Both BYU's A3B and MBZUAI's K2 Think represent the vanguard of this new era, delivering frontier-level reasoning, often outperforming much larger counterparts, all while championing openness and accessibility. These are not just incremental improvements. They are foundational breakthroughs that promise to make advanced AI more powerful, more accessible, and ultimately more useful to everyone. What do you think? Are these lean, smart models showing us the true future of reasoning AI? Or is the pursuit of raw size still the ultimate goal? Share your thoughts in the comments below. If you found this insight interesting, make sure to hit that like button and subscribe for more deep dives into the world of AI. Thanks for watching, and I'll catch you in the next one.